Good morning, everyone. My name is Joseph Chatelon, and with Jacques Henri Balbi, we come from the University of Corsica to talk about physics, and more precisely, how 10 years of physical assumptions led to the development of the Balbi model from laboratory scale to field scale. So, 10 years ago, the main part of fire propagation models was split up in empirical models, for instance, the well-known Rothermel model, and complete physical models, the so-called multiphasic models integrated into simulators such as Firestar, Firetech, or WFDS. Simplified physical models were yet another type of model, for instance, Pani, Peterson, and Koo, which were physics-oriented enough with a computational time close to zero. Our goal at the University of Corsica was to build a simplified surface fire propagation model, no crown fires, that could be used by people involved in firefighting or in fire management. So, this model had to be physics-oriented, three-dimensional, faster than real-time, and provide a good accuracy. The use of simplified physical laws had to give the main physical characteristics of the fire front: rate of spread, flame tilt angle, flame temperature, etc., as a function of the wind speed, the terrain slope angle, the fuel moisture content, and other fuel characteristics. This model was built in 5 steps, from a simple model to a complete model working at the field scale. So the point is how to obtain a simplified physical model. The first important thing is to avoid partial differential equations, which need strong assumptions on the gas phase. Then we have to consider average values of the variables, for instance, the mean flame temperature. And third, we have to consider simplified physical laws, for instance, simplified mass or energy or preheating balance. Finally, the rate of spread appears to be the solution of an algebraic equation. The first operational model took into account 3 energy transfer modes: flame-based radiation, I mean the radiation from the fuel burning particles area. The burning fuel unburned fuel is assumed to be a black radiant panel, and we use a usual Stefan Boltzmann modeling. Flame radiation, with the flame as a gray radiant panel. And convective cooling in front of the flame. This cooling leads to a strong assumption: the flame radiation only impinges the unburned fuel under the flame. A simplified preheating balance gives the expression of the rate of spread as the sum of the 2 previous contributions. A velocity composition law provides the definition of the flame tilt angle, which depends on the terrain slope angle, the normal component of the wind velocity, and the upward gas velocity. This model was confronted to later experiments with success, but some weaknesses remain. Some equations of the model come from empirical laws. For instance, the flame height is computed with the McCaffrey correlation. Another weakness lies in the definition of flame radiation. And last but not least, the simplified model has 3 model parameters. Obviously, it needs to be improved. 3 years later, 3 improvements were made. First, we changed the McCaffrey correlation for a physical law obtained with a simplified vertical momentum balance. We also came up with a better modeling for the radiative fraction, and we introduced a fresh cooling which models the backfire better. This improved model was confronted to a set of laboratory experiments with strong winds up to 11 meters per second and non-parallel wind and slope. However, this model still neglects convection and then poorly represents laboratory experiments with well-ordered vertically oriented fuel bed. This improved model has been used in several manners over 4 years. The first one concerns its integration into the for-fire simulator. It also acted as input data for our analytical model for acceptable safety distance. This part will be taken up by my friend Jean-Louis Rossi in his talk this afternoon. Thanks to the model, we were able to find two non-propagation criteria, a condition on the extinction moisture and another on the packing ratio. Finally, the last development concerns eruptive fires. We believe, as Viegas did, that the convective flow induced by the fire is responsible for eruptions triggering. We produced a physical modeling of what we called induced wind, and our model is able to compute the threshold slope angle from which eruption is sure. I don't get into the details because I will make a talk about eruptive fires on Thursday, and more precisely on the improvements leading to an analytical expression of this threshold slope angle. The next step is about the development of a convective model. The point is to determine what convection we are talking about. When we talk about convection, we mean the flow of the hot gases. So, as to check the validity of a convective model, this model has to be confronted to experiments with well-ordered and vertically oriented fuel beds. Indeed, many authors, from Wolf, Carrier and Fendel to Mark Finney, proved that convection is the dominant heat transfer mode in this type of experiments. So, with those specific fuel beds, radiation from the flame base is still considered, but is expected to be not very important because of the well-ordered fuel particles. Flame radiation impinges a very small surface of the fuel bed because of the verticality of fuel particles, and then will be neglected. As several authors did, we consider that the flame is quasi-laminar in its first half above the vegetal stratum, and then it acts as a barrier to the airflow. So we take into account the flow inside the flame base. A gas particle inside the flame base is subjected to wind speed and upward gas velocity. Some gas particles go out of the flame base through its top and then go into the flame. But some gas particles go out of the flame base through the burning-unburned fuel interface. This hot gases flow creates a contact flame which ignites the unburned fuel. I think everyone has recognized the fingers of fire observed by Rothermel and Anderson. We have confronted this model to 172 laboratory fires picked up in the literature. We can observe the good agreement between predicted and observed rate of spread, with a very small normalized mean square error, a fractional bias close to zero, and the Pearson's correlation coefficient close to unity. But the most important thing is that the model has no model parameters. The only changing characteristics from one experiment to another are wind velocity, terrain slope angle, and fuel characteristics. As we have a convective model and a radiative model, we combine them to obtain a complete model. Note that the radiative model was improved with the removal of all the model parameters. One example is the radiant coefficient. 10 years ago, it was a fitted coefficient. Then we produced a physical modeling of this coefficient with a model parameter, which finally disappeared. Okay, now we have a complete model with radiation and convection, but what is the dominant heat transfer mode? In fact, the rate of spread is an increasing function of the wind velocity. After a fast increase, the rate of spread reaches a plateau, which is obtained for a threshold value of the wind speed. Below this value, we can say that flame radiation is negligible. Above this value, the competition between radiation, flame radiation, and convection involves a negligible flame base radiation. This complete model was confronted to the 357 laboratory fires carried out by Catchpole et al. We can observe a small error, less than 8%, a light underestimation, and a Pearson's correlation coefficient close to unity. Those experiments are very important because Catchpole and her co-authors gave all the fuel characteristics needed by our model. This year, we confronted our model to the field scale. When the fuel bed is a homogeneous vegetal stratum, the model gives very good results. Here are the results on the fires performed by Gould. But when the vegetal stratum is composed of dead and living particles, we need to make a new assumption. Indeed, the dead part of the fuel is the mainspring of the spread, whereas the living part of the fuel acts as a brake for the spread. So convection will be changed in this case. Actually, in order for the living part of the fuel to be dried out and pyrolyzed, a flame must exist in the base. So we make this new following assumption with no convection in case of this flame depth is equal to 0. This field scale model was confronted to almost 200 field fires, mainly shrubland and grassland fires, and the results are encouraging with an error below the 20% level and a very good correlation. As a conclusion, we can say that 10 years ago we started with a simplified semi-physical surface fire propagation model with many weaknesses, and we finished with a simplified physical model which takes into account radiation and convection, and above all without any model parameters. The radiant coefficient is an example of this work. From a fitted parameter, it gained a physical meaning. Obviously, taking convection into account and the removal of all the model parameters, thanks to physical modeling, are the two major improvements. We confronted the model to several fires with an average error of 8% at the laboratory scale and about 20% at the field scale. Thank you for your attention.